You will need to draw an auxiliary view when you need to show a feature that's not on an orthographic top, front, or side view. And to think about laying out an auxiliary view, let's remember what we know about the glass box. This is how we lay out our views. And so we have our object inside the box, and we trace the view on each side of the flaps, and we unfold the flaps, and there we are. There are our views, and they are all aligned. Okay, what if you have an object that has an inclined surface, like this one has, a sloping surface, and you put it inside the glass box and you trace all those views, and here are the views you get. The problem with this glass box situation is that none of the views of that inclined surface are true size and shape. They are all what is called foreshortened. So in the top view, it's the right width, but it's been squished side to side. And in the front view, it's the right width, but it's been squished up and down. It's foreshortened. And ASME says we have to dimension our features in the view where they appear true size and shape. So what do? What we do is we create another view called an auxiliary view, and it's an orthographic view. It's at right angles to something or other. It's just not one of those standard top, front, side views. And how we do that is we use our good old glass box again, but we add another flap to the glass box. We add a flap that is parallel to the inclined surface we want to draw. And again, of course, this glass box is imaginary, that we are visualizing this in our mind. So in our mind, we imagine there's a sloping glass box side, and it's parallel to that sloping surface we want to draw. And then we unfold the flaps of this box just like always. Well, I should have said, we trace each of the views in each of the flaps, then we unfold the flaps, and this inclined flap automatically winds up with an auxiliary view, which is true size and shape. It's a reflection exactly of that inclined surface. Here we are. That might not be such an issue when you have just a flat rectangular surface, but what if you have an inclined surface with a hole in it, and you need to dimension for your machinist where this hole is located and how big it is? And if you just have a top and a side view, that surface is foreshortened and that hole looks like an ellipse, and this is not good. So there's no way to dimension for your machinist where this hole is. Instead, you create an auxiliary view. So this view shows this inclined surface true size and shape. And look, there's that hole. Now it looks like a circle, and it's in the correct location. And there are those corner radii, they're correct. Now you could dimension it. Some drafters, especially old-time drafters, like to think about fold lines in their glass box. So here is our object where we're going to start drawing our auxiliary view. And the key idea is to think parallel perpendicular. Every surface, every line in your auxiliary view is going to be parallel or perpendicular with this inclined, with this inclined edge view. So that's where you start. You find the view where that inclined surface looks like an edge, and you run construction lines perpendicular to that edge. And then your auxiliary view has lines that are either perpendicular to that edge view, or they are parallel to that edge view. Here's the fold line that some drafters, especially old-time board drafters, like to do. And the reason they like to do that is because when you draw your auxiliary view, you are measuring some distances, depths, widths, and so on and so forth, what they say one view back. So here's the auxiliary view. We can't measure that depth from our front view, so we go one layer back to our top view or one layer back to our side view. And that depth is going to be the same dimension, the same size in each of those views. Personally, I don't do the fold line, but there you are. Some people do. Now, remember that our job is to communicate clearly to our internal customer, who might be a machinist or a fabricator or an assembler. If you draw a full auxiliary view where, yeah, this surface is parallel and perpendicular to the inclined edge view, but then you're also projecting all the visible edges, you get a full auxiliary view. And now, although your inclined surface is true size and shape, your other surfaces are foreshortened, like this. The flat plate that makes up the body of this part is foreshortened in the auxiliary view. A better solution is to draw something known as a partial auxiliary view. And here is this same part on the bottom of the slide, where now we are only drawing an auxiliary view of that inclined surface that we couldn't show accurately in any other view. So notice we have not projected lines from all these other corners. We've just projected lines from that one inclined surface. Here's a part that has, it's like a U-shaped bracket. One of the U-shaped legs is also sitting at an angle, and then there's a hole in each of those three legs. And this tall one here on the left is radiused. Okay, so if we want to dimension this front plate, we want to show where that hole is located. We'll draw an auxiliary view, parallel and perpendicular. But if we draw a full auxiliary view and project every single point, what we get is confusion. I mean, look at that thing. That is hard to interpret. And if our job is to communicate clearly, we would be better making a partial auxiliary. What we want to communicate is, what does this sloping face look like and where is the hole? So here is a partial auxiliary that shows that true size and shape. And if you look at the ASME standard, the one that has views in it that includes auxiliary views, you will notice that the ASME standard does not show full auxiliary views. They show partial auxiliary views because they rightly realize that these views are much more clear if you just do the partial. And here in the top view, the top picture, here's a U-shaped bracket. These are not 90-degree angles, they're sharper angles, and each side is different. If you want to show each side for your fabricator, you would make two different partial auxiliaries and then a front view that shows the formed angles. That's very clear to anyone who knows how to do blueprint reading. Here is the drawing that we're going to do for the assignment for this. And notice at the bottom of the slide, I refer you to two things. One, we'll look at a CAD 3D model. So let's go look at that. And then in the next video, we'll look at CAD drawing. This is a 3D drawing, and the reason this looks so weird is because if you go to model space, This is actually a 3D model, and if I get my 3D orbit command and rotate it, you can see, oh, that's what our part looks like in 3D. And then in paper space, I made 4 separate viewports, and in each viewport I viewed this 3D object from a different direction. So here, we're not drawing the side view, but if we were, here it is, and you'll notice that, oh dear, stop that. Here, I don't know if I can get the 3D orbit to work here. 3D orbit. So I'm actually viewing a side view of this solid 3D object. So my only point in making this for you is just to give you a place where you can go and turn this object all around and see where that slot comes out and what it looks like from different views. In the next video, we are going to go look at a 2D drawing, and I've made a PDF of this drawing for you. So this is what your drawing should look like. In the next video, we'll come in and look at how might you lay this thing out.